lesson today is about rotational kinetic energy. The formula for regular kinetic energy is 1/2 mv squared. Okay, we're going to start calling this kind of kinetic energy one of two things. We'll call it translational. All right, that means for something that is, moving in a straight line, or therefore we'll sometimes call it linear kinetic energy. Either of those two terms is acceptable for this. Most commonly, I'm going to use the subscript, as I've been using for years on this, K trans for translational. That's the subscript I've been using forever, and that's what it says in all the notes packets, so that's what I'm using. Anyway, so translational kinetic energy is the kind of energy that something has when it's moving in a straight line. Rotational kinetic energy is the kind that's new today, and that's, the identical formula, but replace all of the linear things with their rotational analog. So instead of mass, you would use moment of inertia. Instead of angular velocity, you would use omega. Instead of V, you'd use omega is what I mean to say. Okay, so 1/2 I omega squared is your formula for rotational kinetic energy. We will be using this for really for three kinds of questions, one of which I'm going to cover in this video. First kind is you've got a terrible looking pulley, whatever, and there's some kind of a weight which is going to fall and make the pulley rotate. In the last homework, you guys are doing problems with torque and pulleys, where you figure out the angular acceleration of the pulley or the linear acceleration of the mass as it falls. Well, all right, these two approaches are kind of complementary. We're going to use an energy approach to figure out something like, how fast will this weight be falling after it has descended some height h, whatever that is? Or maybe figure out what's the angular velocity of the pulley after the weight has descended some height h. All right, that type of problem I will cover in class right now on Zoom. The other two kinds of questions that you'll see in the homework are these. The falling bar, right? Pivot there, all right, and then of course the bar falls and ends up in like a vertical orientation kind of a thing. Okay, that one I will not cover in class synchronous. That will be covered in a video, which I'm going to have you watch. And then the third kind of problem is for something which is rolling downhill. All right, so here it goes, rolling down the hill, and of course, since it's rolling, it has translational kinetic energy because it's moving, and also it has rotational kinetic energy because it's rolling. All right, for each of these question types, we need to think about what kind of these energies are present for each of those systems. For all of them, the initial condition is you start with gravitational potential energy, right? Everything's going to start with gravitational potential energy. And then after some amount of time, something has fallen some distance, and we will think about it as having either rotational kinetic energy or a mixture of translational and rotational kinetic energy, one or the other. All right, so I'm going to present the sort of general scheme for how you approach each of these questions, and then I'll go into the specifics of doing the problem with the pulley. For the pulley problem, you start with gravitational potential energy. Which of the two objects, the pulley or the little weight, which of them initially has gravitational potential energy? The weight. Okay, so we would say starts with gravitational potential energy, and it's the weight that has it. All right, after the weight falls some distance, it will, well, let's see, it's moving downwards. So it will have translational kinetic energy. And also the pulley will have rotational kinetic energy. All right, we'll get into the nitty-gritty of that in a little bit. All right, for the falling bar problem, again, I know this is going to be covered in detail in another video I'm going to have you watch, but the system starts with gravitational potential energy. In this case, the final energy is only rotational kinetic energy. We do not think of the bar as having translational kinetic energy because the bar is not really going anywhere, right? There's no object which is translating or moving forwards. In the case of the bar, we don't think of it as having translational kinetic energy, largely because the pivot doesn't move. If the pivot doesn't go anywhere, then it doesn't have translational kinetic energy. All right, and then for the thing that's rolling down a hill, again, this is going to be covered in another video, but it starts with gravitational potential energy at the top. And then when it gets, down some distance, it's rolling. So it's got rotational kinetic energy, but it's also moving. So it's going to have both kinds, translational and rotational kinetic energy. All right, let's do the pulley problem. In general, we're going to say the pulley has a mass of m and a radius of r. Okay, the little weight here has a mass of little m. And the goal here is going to be find the speed of the mass after some amount of time, or not time so much, but after it's fallen, some height h, right? So starting point, we would say the weight begins with gravitational potential energy. All right. At the end, after it has fallen some distance, and now we're looking at this moment, the gravitational potential energy that we started with has now gone into two forms. One of them is the translational kinetic energy of the little weight. And the other form is the rotational kinetic energy of the pulley. All right, let's plug in formulas for these things. For the gravitational potential energy on the left side, that would be, well, we know the formula is mgh, but I'm using specifically little m here because the m is for the mass of the little weight, right? If I put in big M, that would be wrong because the pulley doesn't, it has gravitational potential energy, but it doesn't change because it doesn't fall. So we ignore the pulley for gravitational potential energy. All right, for translational kinetic energy, again, we know the formula is 1/2 mv squared. Specifically, though, we're using little m because the weight is the thing that has translational kinetic energy. The pulley doesn't go anywhere, so it doesn't have any translational kinetic energy. All right, the rotational kinetic energy is obviously all in the pulley. So we write down that formula, 1/2 I omega squared. All right, next step. I'm going to do a couple of things in here which you do in mostly every rotational kinetic energy problem, and that is this. Thing one is we got to substitute in for the moment of inertia. Depending on what the pulley is, we'll have a different moment of inertia formula. Okay, so in this case, that's going to be, we'll say 1/2 big M r squared. This is assuming that this is a solid cylinder. Pulleys are always going to be some kind of a cylinder, but it could be a hollow cylinder or something like that. So whatever, in this case, it's a solid cylinder. All right, the other substitution you're going to make, and this is just like going to happen in every single rotational kinetic energy problem ever, is I've got to actually replace the omega with something because I don't know V. I'm trying to find V. I also don't know omega, the angular velocity of the pulley, and they're related to each other. So I can't solve for one without solving for the other. So that would seem to be a problem because I've got, oh no, two unknowns. I don't know omega, I don't know V. How can I solve for anything? Well, they are related by this formula, V equals omega R, which should be very familiar to everybody because we've been using it throughout this unit so far. So that means that omega would be V over R. In this case, the little r is the radius of the pulley, right? Distance from the pivot, where the string is pulling on the edge of the pulley, is the radius of the pulley. And of course, that's squared, so there. All right, let me go ahead and copy down the rest from the line above. Okay, so now things that happen. Well, this last part with the v over r and then that getting squared means effectively it's 2v squared over r squared. So you should notice, oh my goodness, the radius of the pulley cancels out. Great, it cancels. So now we just have mgh equals 1/2 v squared plus 1/4 big M v squared. All right, from here, you could probably see your way to solving for v, right? You know, combining like terms and factoring or whatever is necessary for the question. A lot of the time, they'll do something like say, oh, by the way, big M, the pulley, is like equal to 8 little m or something like that. Maybe, right? All right, now if they said something like that, then at this point, we could say that we could replace this big M here with 8 little m. And then I guess 8 over 4 is 2. So we could, another line down here, mgh equals that right there. The factor of little m cancels out everywhere. All right, and then that's going to leave us with, let's see, gh equals 2.5. So what is that? 5/2 v squared. And then you can solve for v. All right, I feel like I didn't probably need to go into the specifics of big M equals 8m, but I wanted you to see what a common kind of a symbolic question might look like with this, where you substitute in and simplify it all the way down. So our final answer for this particular case would be square root of 2gh over 5. And that's our answer. All right, obviously the answer is going to depend on exactly like how big M is, right? Maybe it's a numbers problem and we don't need to do all the symbolic stuff, but the basic process here is the same, right? For every pulley problem, the first line that I did, going to be the same, every pulley problem. Second line, going to be the same, every pulley problem. Third line, depending on what they tell you, there will be some changes, like maybe it's not a solid cylinder. But pretty much every time you're going to do that step where you replace omega with V over R. Okay, and then from there, the particulars of the question take over and you solve for whatever you're supposed to solve for.